should be corrected. If there are no faults in the error correction circuit itself. If the input is perfect, meaning it lies in the code space, and one fault occurs during error correction, output should have at most one fault.
I see. So it's both fault tolerant. Like the circuit is fault tolerant.
Yeah, so what I'm saying is the total number of faults, either input faults or internal faults, is at most one. But the input faults are corrected. Faults during the circuit, they can't be corrected. I mean, you can't, because there's always like a fault at the very end, it's hopeless, right?
That's true, yeah, sorry.
So we only hope to correct the input faults. The faults in the middle, if we can correct them, that's good. If we can't correct them, we just don't want them to spread. And this definition, again, it naturally generalizes. So if we want to do 2 fault tolerance or 3 fault tolerance, it becomes more complicated. You say that the faults can be partitioned between input faults and these faults. And these faults have to be corrected, and the output should have weight. The weight of the output error should be most of the number of internal faults. Or generally, weight of output error should be less or equal to number of internal faults, provided number of input faults plus number of internal faults is less or equal to whatever distance you want to get to, d minus 1 over 2. Yeah.
So I have questions. So can I design some threshold just not to so when we are doing the measurement, can we just not exactly measure whether it's 0 or 1? So
What do you want to do?
So like approximate projection to 0 or 1. So we can tolerate some errors.
Maybe. I mean, there are other things. There's also things where you do error correction sort of continuously in time. So you try to measure, you do with your continuous measurements. And this is the advantage of several things. One is you could just imagine what's called a Zeno effect, the watch pot effect, where even though the state is being pushed out of the code space, you're projecting it over and over into the code space. So overall, in that case, maybe you don't have to apply any corrections at all because you're pushing it into the code space automatically. Or there are some continuous feedback schemes. These kinds of schemes are the most common. Yeah. Okay. So that hopefully this gives you some idea. So it's not enough just to measure the syndrome. You have to maybe measure the syndrome redundantly to make it fault tolerant. That's one thing I wanted to say. The second thing, which you don't see in this example, is that, so in this example, I'm just measuring parities of 2 qubits at a time. And that's fine, because that's nice, because it meant that a z error here could spread to most of 1 z error on the data. But it wouldn't work if I were trying to measure the parity of more qubits at a time. For example, if I were trying to measure the parity of 4 qubits, like say this were 7 qubit Stein code, and I wanted to measure the parity of 4 qubits at a time to measure one of those z stabilizers. The problem is, so I'd put a 0 here, and then I'd have 4 CNOT gates down into it. The problem is a single z fault in the middle could spread backward to weight 2 z error in the data. So that's a problem, and fortunately there's an easy solution, which is instead of computing parities into one qubit like this, we'll prepare a 4-qubit cat state fault tolerantly using one of these circuits we just came up with, and then apply C0 gates into the cat state transversely, so you don't have to worry about area spreading. Okay, so I'm out of time. I can talk more about that or not. Hopefully, some of the point that I would hope to get across is just that this is complicated. You gotta check the cases and figure things out depending on the code. Everything's different. Yeah.